Tonight, we're going to explore something that sounds like it should be simple: the size of the universe. But here's what most people don't realize. The moment you start actually measuring things, when you begin comparing one scale to another, you run into something deeply unsettling. Almost everything we can see, every star, every galaxy, every cluster of galaxies, all of it combined makes up less than 5% of what exists. And even that visible part is just a tiny bubble, floating inside something that may stretch on forever. By the end of tonight, you're going to understand not just how incomprehensibly vast the universe truly is, but why everything we've ever observed may represent only a small fraction of what's really out there. Before we begin, if you enjoy exploring the depths of space as much as we do, take a moment to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now let's begin. Let's start with something familiar, something you can actually picture: Earth. Our planet measures about 12,742 kilometers across at the equator. That's large enough that if you tried to walk all the way around it, walking 8 hours a day at a steady pace, it would take you more than a year. Even if you could drive non-stop at highway speed, it would still take roughly 2 weeks. From where you're sitting right now, Earth feels enormous. There are mountains you'll never climb, oceans you'll never cross, entire continents you may never visit. The sheer size of our world is something most people never truly grasp, because we only ever experience tiny fragments of it at a time. But Earth isn't alone. It sits inside a solar system with 7 other planets, all orbiting a star so large that you could fit about 1.3 million Earths inside it. Our sun measures roughly 1,992,000 kilometers across. That's 109 times wider than Earth. If you lined Earth up side by side across the sun's diameter, you'd need 109 Earths. And remember, Earth already feels massive from our perspective standing on its surface. But the distances between the planets in our solar system are even more staggering than their sizes. Earth orbits the sun at an average distance of about 150 million kilometers. This distance defines what astronomers call 1 astronomical unit, or AU. Light, traveling at about 300,000 kilometers per second, takes roughly 8 minutes and 20 seconds to cross that gap. When you look at the sun, you're not seeing it as it is right now. You're seeing it as it was more than 8 minutes ago. Jupiter, the largest planet in our solar system, orbits at about 5.2 AU from the sun, roughly 778 million kilometers away. Light from the sun takes about 43 minutes to reach Jupiter. Neptune, the most distant planet, sits about 30 AU from the sun, roughly 4.5 billion kilometers away. Light takes around 4 hours to travel from the sun to Neptune. But here's where things start to get interesting. The solar system doesn't end at Neptune. Far beyond the planets lies a region called the Oort cloud, a vast spherical shell of icy objects that surrounds the entire solar system. The Oort cloud begins around 2,000 AU from the sun and may extend outward to as far as 100,000 AU. That outer edge is roughly 1.6 light years away. A light year is the distance light travels in 1 year, about 9.46 trillion kilometers. The Oort cloud marks the true boundary of the sun's gravitational influence, the region where objects are still loosely bound to our star. And here's the key point. The Oort cloud extends almost halfway to the nearest star. That nearest star is Proxima Centauri, part of a triple star system called Alpha Centauri. Proxima Centauri is about 4.24 light years away, roughly 40 trillion kilometers. If you could somehow travel at the speed of a commercial jetliner, about 900 kilometers per hour, the journey would take around 5 million years. Let's put that distance into perspective with a scale model. Imagine shrinking the sun down to the size of a basketball, about 24 centimeters across. In this model, Earth would be a tiny bead, just 2 millimeters wide. And where would that bead be? Not next to the basketball. It would be 26 meters away, the length of 2 school buses parked end to end. Already, the emptiness of space becomes obvious. Now ask yourself, where would the nearest star be in this model? Not across the room, not across the city. You'd have to travel nearly 7,000 kilometers. Feel if your basketball-sized sun were sitting in London, the nearest star would be somewhere in New York. 2 basketballs separated by the width of the Atlantic Ocean. And remember, these are the closest stars to each other. Most stars are separated by distances far greater than that. This is the first scale we need to truly understand. Stars are separated by distances so immense that even light, the fastest thing in the universe, takes years to travel from one star to another. And our Sun is just one of hundreds of billions of stars in our galaxy. The Milky Way, our cosmic home, is a barred spiral galaxy containing somewhere between 100 and 400 billion stars. That range is enormous because it's incredibly difficult to count stars when you're sitting inside the galaxy itself. It's like trying to count every tree in a forest while standing in the middle of it. Nearby trees block your view of everything farther away. But the exact number matters less than the scale. Hundreds of billions of stars, each separated from its neighbors by light years of mostly empty space. The Milky Way measures about 100,000 light years across and roughly 1,000 light years thick in most regions, though the central bulge is much thicker. Viewed edge-on, it would resemble a flat disk with a swollen center. Our Sun sits about 26,000 light years from the galactic center, roughly halfway out toward the edge, in a relatively calm region between spiral arms. And the Milky Way is rotating. Our Sun orbits the galactic center at about 828,000 kilometers per hour. Even at that incredible speed, it takes roughly 225 million years to complete a single orbit. The last time the Sun was in this exact position, dinosaurs didn't exist yet. Earth was in the Triassic period, and the continents were still fused together into one massive supercontinent called Pangaea. Now, let's zoom out again. The Milky Way isn't alone. It's part of a small collection of galaxies called the Local Group. The Local Group contains about 50 galaxies, most of them small dwarf galaxies. The 3 largest members are the Milky Way, the Andromeda Galaxy, and the Triangulum Galaxy. Andromeda is the largest of the 3, containing about 1 trillion stars and measuring roughly 220,000 light years across. The Milky Way is the second largest. Triangulum is smaller, with around 40 billion stars. The distance between the Milky Way and Andromeda is about 2.5 million light years. Think about that. Light, moving at 300,000 kilometers per second, takes 2.5 million years to travel from one galaxy to the other. Even if you could travel at the speed of light, which physics tells us is impossible, it would still take 2.5 million years. At the speed of a spacecraft like Voyager 1, which travels at about 61,000 kilometers per hour relative to the Sun, that journey would take roughly 44 billion years, more than 3 times the current age of the universe. The entire Local Group spans about 10 million light years. That's considered small as galaxy clusters go. Some clusters contain thousands of galaxies packed into similar volumes of space. But even 10 million light years is an almost incomprehensible distance. Here's another scale comparison. If the Milky Way were the size of a dinner plate about 25 centimeters across, the Local Group would be roughly 2.5 meters wide, and the Andromeda Galaxy would be another dinner plate sitting about 63 centimeters away. But we're not finished. The Local Group itself is part of a much larger structure known as the Virgo supercluster, also called Laniakea. Laniakea contains roughly 100,000 galaxies spread across about 520 million light years. The name Laniakea comes from Hawaiian and means immeasurable heaven, which is fitting because mapping this structure required decades of work by hundreds of astronomers. Laniakea isn't just a random collection of galaxies. It's a coherent structure held together by gravity. Galaxies within Laniakea move through space along vast filaments and sheets, all flowing toward a central region known as the Great Attractor. The Great Attractor is a gravitational anomaly located in the direction of the constellations Centaurus and Hydra. It's pulling the Milky Way and millions of other galaxies toward it at about 2 million kilometers per hour. No one knows exactly what the Great Attractor is. It lies hidden behind the plane of the Milky Way, obscured by the dust and stars of our own galaxy. We can't see it directly. We only know it exists because we can measure how galaxies are moving and calculate where they're being pulled. Whatever it is, it contains the mass of tens of thousands of galaxies, possibly a massive concentration of dark matter, or an enormous cluster of galaxies hidden from view by our own. Take a moment to consider how far we've come. We started with Earth, then the solar system, then the Milky Way, then the local group, then Laniakea, with its 100,000 galaxies flowing towards the Great Attractor. And yet, even Laniakea is just one supercluster among millions in the observable universe. And the observable universe itself is far larger than most people imagine. The observable universe is defined by the cosmic horizon, the maximum distance light has been able to travel since the beginning of the universe. The universe is about 13.8 billion years old, so you might assume the observable universe has a radius of 8 billion light years. But it doesn't. The universe has been expanding since the Big Bang, and that expansion has been accelerating. Space itself is stretching, carrying distant galaxies farther and farther away. When we account for this expansion, the observable universe has a radius of about 46.5 billion light years. That means the observable universe is roughly 93 billion light years across, about 880 billion trillion kilometers. That number is so large it becomes meaningless. Our brains simply didn't evolve to comprehend scales like this. We can write the number down, we can do the calculations, but we can't truly visualize what it means. And here's what makes this even more mind-bending. The observable universe contains an estimated 2 trillion galaxies. That's our current best estimate based on deep field observations from the Hubble Space Telescope and other instruments. Each of those galaxies contains hundreds of billions of stars. Let's try one more scale comparison, if only to make this slightly less incomprehensible. If the entire observable universe were shrunk down to the size of Earth, about 12,842 kilometers across, then the Milky Way galaxy would be about 14 micrometers wide. That's smaller than a human red blood cell, which measures around 7 to 8 micrometers. You couldn't see it with the naked eye. You'd need a microscope just to detect it at all. And remember, the Milky Way contains hundreds of billions of stars. Each of those stars, including our Sun, would be far too small to see, even with the most powerful microscope ever built. Or consider this. If the Milky Way were the size of a coin about 2 centimeters across, then the observable universe would be about 2,000 kilometers wide. That's roughly the distance from Los Angeles to Denver, or from London to Rome. Imagine standing in Los Angeles, holding a coin that represents the entire Milky Way galaxy, with all its stars, planets, and history, while realizing that the observable universe stretches all the way to Denver in every direction, filled with trillions of other coins, each one representing another galaxy. But we're still not done, because the observable universe is not the entire universe. It's only the part we can see. The actual universe is almost certainly much larger, possibly infinitely larger. The cosmic horizon limits how far we can observe, but it doesn't limit how far space itself extends. Beyond the observable universe, there is more space, more galaxies, more stars. We just can't see them, because their light hasn't had time to reach us yet. So how much larger is the actual universe compared to the observable universe? We don't know. It could be twice as large. It could be 1,000,000 times larger. It could be infinite. Current observations suggest the universe is either perfectly flat or extremely close to flat. And a flat universe extending infinitely in all directions is fully consistent with everything we've measured. If the universe is infinite, then the observable universe, vast as it is effectively a rounding error compared to the whole. A tiny bubble floating in an endless ocean of space. Think about what that means. Everything we've ever seen, every star in the night sky, every galaxy photographed by our most powerful telescopes, every structure we've mapped, from the local group to Laniakea, to the largest cosmic filaments, all of it exists inside that tiny bubble. And beyond it, there is more, endless more. Galaxies, stars, and planets that we will never see, because the light from them will never reach us. But let's return to what we can observe, because even that is staggering. For decades, astronomers have been mapping the large-scale structure of the universe, determining where galaxies are and how they're distributed. What they've discovered is that the universe isn't uniform. Galaxies aren't randomly scattered through space. They're arranged into structures of almost unimaginable scale. Galaxies group together into clusters. The Milky Way resides in the local group, which is relatively small, but some clusters are enormous. The Coma cluster, for example, contains over 1,000 large galaxies and likely more than 10,000 smaller ones, all packed into a region about 20 million light-years across. The Virgo cluster, relatively close to us at about 54 million light-years away, contains at least 1,300 galaxies, and possibly more than 2,000. And these clusters are themselves organized into even larger structures called superclusters. We've already talked about Laniakea, our home supercluster, but there are millions of other superclusters scattered throughout the observable universe. Each one contains tens of thousands, and sometimes hundreds of thousands of galaxies. The Shapley supercluster, for example, is one of the largest structures ever identified. It lies about 650 million light-years away and contains more than 8,000 galaxies. And superclusters themselves don't exist in isolation. They are arranged into even larger formations known as filaments and walls, vast sheets and strands of galaxies stretching across hundreds of millions or even billions of light-years. One of the most famous examples is the Sloan Great Wall, discovered in 2003. It's a massive filament of galaxies stretching about 1.37 billion light-years across and located roughly 1 billion light-years from Earth. It contains tens of thousands of galaxies. To put that into perspective, if the Milky Way were reduced to the size of a grain of rice, about 2 millimeters across, the Sloan Great Wall would extend farther than 10 football fields placed end to end, roughly 1,600 meters. And that's just one structure. There are many others like it scattered throughout the universe. The largest structure ever discovered is known as the Hercules Corona Borealis Great Wall. This structure is traced by gamma-ray bursts, which likely signal an enormous concentration of galaxies stretching across roughly 10 billion light-years. That's more than 10% of the diameter of the observable universe. It's so large that it challenges our current understanding of how the universe formed and evolved. According to standard cosmological models, structures this vast shouldn't exist. There hasn't been enough time since the Big Bang for gravity alone to assemble something so enormous. And yet, it exists. We've observed it, which means either our models are incomplete, or there's something fundamental about the universe that we still don't understand. Between these filaments and walls lie voids, immense regions of space containing very few galaxies. The Boötes void, discovered in 1981, is a roughly spherical region about 330 million light-years across, with remarkably little matter inside it. It's not completely empty, but it's far less dense than an average region of space. In a volume that size, you'd normally expect to find around 2,000 galaxies. The Boötes void contains only about 60. These voids are, in some ways, even harder to comprehend than the filaments and walls. They are regions where almost nothing exists. Empty space stretching for hundreds of millions of light-years. If you were somehow placed at the center of a void, you would see almost no galaxies in any direction. The nearest ones would be so distant, they'd barely be visible. Even with a powerful telescope, you'd be surrounded by darkness, with only the faint glow of distant structures outlining the edges of the void. Taken together, the large-scale structure of the universe resembles a cosmic web. Filaments and walls of galaxies surround vast voids, creating a pattern sometimes described as cosmic foam, with galaxies concentrated in thin membranes between enormous bubbles of emptiness. This structure formed over billions of years as gravity slowly pulled matter together. In the early universe, matter was distributed almost uniformly, with only tiny fluctuations in density. But those tiny differences mattered. Slightly denser regions had slightly stronger gravity, which pulled in more matter, making them denser still. Over billions of years, this runaway process produced the immense structures we see today. Now let's talk about what we can't see. Because as vast as the observable universe is, and as staggering as these structures are, they represent only a small fraction of what actually exists. So what makes up the rest of the universe? The rest is something else. Something we can't observe directly, but whose existence we know is real because we can measure its gravitational effects. About 27% of the universe is made of dark matter. Dark matter doesn't emit, absorb, or reflect light. It doesn't interact with electromagnetic radiation at all, which means no telescope, no matter how powerful, can see it. We know dark matter exists only because of what it does to the things we can see. Galaxies rotate faster than they should based on their visible mass alone. Galaxy clusters are held together by far more gravity than their stars, and gas can explain. Gravitational lensing, the bending of light around massive objects, reveals far more mass than we can observe directly. Dark matter forms massive halos around galaxies, providing the gravitational framework that holds them together. The Milky Way is embedded in a dark matter halo that extends far beyond the visible disk of stars. That halo contains more mass than all the stars in the galaxy combined, possibly 5 to 10 times more. We are moving through dark matter right now. Earth, the solar system, and the entire Milky Way are immersed in a vast sea of it, but it passes through ordinary matter almost without interacting at all. We don't know what dark matter is made of. The leading idea is that it consists of particles that don't interact through the electromagnetic force. They respond to gravity, and possibly the weak nuclear force, but little else. If that's true, then billions of dark matter particles are passing through your body every second, through the Earth, through everything, without you ever noticing. Scientists have built highly sensitive detectors deep underground, shielded from cosmic rays and other interference, trying to catch a dark matter particle interacting with ordinary matter. Despite decades of effort, nothing definitive has been detected yet. But at least dark matter is still matter. It has mass. It exerts gravity. Its effects can be measured. The remaining 68% of the universe is something even stranger. It's called dark energy, and we understand it even less. Dark energy is what's driving the accelerating expansion of the universe. In the 1920s, astronomer Edwin Hubble discovered that the universe is expanding. Distant galaxies are moving away from us, and the farther away they are, the faster they're receding. This discovery was revolutionary. It implied that the universe had a beginning, a moment when everything was compressed into an unimaginably small, dense state before expanding outward. We call that moment the Big Bang. For decades, astronomers assumed that this expansion must be slowing down. Gravity pulls things together, so the combined gravitational attraction of all matter in the universe should act like a brake, gradually slowing the expansion. The big question was whether the universe contained enough matter to eventually halt the expansion and collapse back inward in a big crunch, or whether it would expand forever, just more and more slowly. Then, in 1998, two independent teams of astronomers studying distant supernovae made a shocking discovery. The expansion isn't slowing down, it's speeding up. The universe is expanding faster today than it was in the past, and that acceleration is increasing. This result was so unexpected, so contrary to what physicists believed, that many initially assumed there must be an error in the measurements. But the data held up. The expansion of the universe is accelerating, driven by something that behaves like a repulsive force, pushing space itself apart. That something is dark energy. We don't know what it is. We can't detect it directly. We can only observe its effects on the expansion of the universe. The simplest explanation is that dark energy is a property of space itself, a kind of energy density inherent to empty space. The more space there is, the more dark energy exists, and the stronger the repulsive effect becomes. As the universe expands, space increases. As space increases, dark energy increases, and the expansion accelerates in a runaway process that appears likely to continue forever. This means the universe is dominated by things we don't understand. Dark energy makes up about 68% of the total energy content of the universe. Dark matter accounts for about 27%. And ordinary matter, the stuff we're made of, the stuff that forms stars, planets, and galaxies, makes up less than 5%. Everything we can see, everything we've ever observed, is a tiny fraction of what exists. So when we talk about the scale of the universe, we're not just talking about distance. We're talking about how little of reality we can actually observe and measure. We're like ants standing on a beach, trying to comprehend the ocean. We can study the sand beneath our feet. We can watch the waves roll in. We can understand our immediate surroundings. But the vast majority of what exists lies beyond our ability to observe or fully grasp. Let's bring this back to something familiar. You're sitting somewhere on Earth right now, reading, watching, or listening to this. Earth is 12,742 kilometers across. It orbits a star that's about 1.3 million times larger by volume, at a distance of 150 million kilometers. That star is one of hundreds of billions in the Milky Way galaxy. The Milky Way is one of about 50 galaxies in the local group. The local group is part of Laniakea, and Laniakea is just one of millions of superclusters in the observable universe. And all of that, everything we can see, represents less than 5% of what exists. At this scale, Earth is effectively nothing. The solar system is nothing. The Milky Way is nothing. Even Laniakea, with its 100,000 galaxies, is just a tiny speck. The largest structures we've ever discovered, filaments stretching across billions of light years, are small features within something vastly larger. But here's the paradox. As small as Earth is, as insignificant as it seems on the cosmic scale, it's also profoundly significant. Because as far as we know, Earth is the only place in the universe where life exists. That may not be true. Given the sheer number of galaxies and stars, it seems unlikely that Earth is unique. The chemical elements that make up life, carbon, hydrogen, oxygen, nitrogen, phosphorus, and others, are common throughout the universe. The physical and chemical processes that led to life on Earth should be able to occur elsewhere. The question is, how often they do. Are there millions of life-bearing worlds in every galaxy? Or is life so rare that only one planet per galaxy develops it? Or is it even rarer than that? We don't know. We've explored only our own solar system in any meaningful detail. And so far we've found definitive evidence of life only on Earth. Mars may have hosted microbial life in the past when liquid water flowed across its surface, but we haven't found conclusive proof yet. Some moons of Jupiter and Saturn, like Europa and Enceladus, contain subsurface oceans that might harbor life, but we haven't been able to explore them directly. So for now, Earth remains a tiny, fragile island of life in an unimaginably vast universe. One small point of awareness inside a reality far larger than anything we can truly comprehend. And beyond our solar system, we've already identified thousands of exoplanets, planets orbiting other stars, including many that are roughly Earth-sized and located in the habitable zone, where liquid water could, in theory, exist on the surface. But we still can't tell whether any of them actually host life. Not yet. So for now, Earth remains unique. It's the only place we know where the universe has become aware of itself. The only place where matter has assembled into something complex enough to look back at the cosmos and understand what it's seeing. That's extraordinary. That's what makes Earth precious, even though it's so small. Carl Sagan famously called Earth a mote of dust suspended in a sunbeam in his book Pale Blue Dot. He was referring to a photograph taken by the Voyager 1 spacecraft in 1990, when it was about 6 billion kilometers from Earth. From that distance, Earth appears as a tiny pale blue dot, barely visible, less than a single pixel in the image. And Sagan wrote about how every human who ever lived, every civilization, every war, every moment of triumph and tragedy, all unfolded on that tiny dot. It's a humbling perspective, but it's also an empowering one. Because if we can understand the scale of the universe, if we can truly grasp how vast it is and how small we are in comparison, then maybe we can also understand how precious our small world really is. Maybe we can see past petty differences and recognize that we're all on this tiny planet together, drifting through an immense and mostly empty universe. And the scale of the universe tells us something else too. It tells us something about the nature of existence itself. Space is mostly empty. The distances between objects are enormous compared to the sizes of the objects themselves. And this isn't just true on the cosmic scale. It's true all the way down. Even atoms, the basic building blocks of matter, are mostly empty space. An atom is about 100,000 times larger than its nucleus. If you could remove all the empty space from atoms and compress Earth down to nuclear density, the entire planet would be only about 180 meters across. All the matter in your body, compressed the same way, would fit on the head of a pin, and you'd weigh the same. All that mass condensed into an almost unimaginably tiny volume. The universe is structured across many levels of scale. Quarks combine to form protons and neutrons. Protons and neutrons form atomic nuclei. Nuclei and electrons make atoms. Atoms form molecules. Molecules form cells. Cells form organisms. Organisms live on planets. Planets orbit stars. Stars gather into galaxies. Galaxies cluster into groups and clusters. Clusters assemble into superclusters. Superclusters stretch into filaments and walls. And beyond that lies the observable universe. And beyond that, possibly an infinite universe. At every scale, emptiness dominates. The gaps between things are the main feature. Matter is rare. Structure is rare. And yet, within those rare pockets of structure, something astonishing becomes possible. Complexity, life, consciousness, civilization, the ability to ask questions about the universe and actually discover answers. Now let's talk about the future of the universe. Because understanding scale isn't only about distance, it's also about time. And it's about where all of this is heading. The universe is about 13.8 billion years old. That sounds like a long time, and by human standards, it absolutely is. But the universe has an almost unimaginable amount of time still ahead of it. Stars, like our sun, will keep burning for billions of years. The sun itself has about 5 billion years left before it runs out of hydrogen fuel in its core and begins swelling into a red giant. Eventually, far smaller stars, red dwarfs, which make up the majority of stars in the universe, will keep shining for trillions of years. The smallest red dwarfs may last 10 trillion years, or even longer. But eventually, even they will burn out. Star formation requires gas, mostly hydrogen and helium, and that gas is being used up. Every time a star forms, some of that gas is converted into heavier elements. When massive stars explode as supernovae, they scatter those heavier elements into space, where they mix with what remains and help form new stars. But each cycle consumes more of the available gas. Some of it gets locked away in stellar remnants, like white dwarfs, neutron stars, and black holes. Some gets thrown out of galaxies entirely. Over time, the universe will simply run out of the raw material needed to build new stars. Estimates suggest that star formation will reach its peak within the next trillion years or so, and then slowly decline. And by about 100 trillion years from now, star formation will have essentially ended. The universe will enter what's known as the degenerate era, a period when the main objects left are stellar remnants. White dwarfs, the cooling cores of dead stars. Neutron stars, dense remnants left behind after supernova explosions. Brown dwarfs, failed stars that never became massive enough to ignite sustained fusion. And black holes, regions of space-time where gravity becomes so intense that nothing can escape. And over even longer timescales, even those remnants won't last forever. Protons, the particles that make up atomic nuclei, are thought to be unstable on extremely long timescales. Current theories suggest that protons might decay with a half-life of about 10^34 years. That's a 1 followed by 34 zeros. And if that's true, then after around 10^40 years, nearly all ordinary matter would have decayed into radiation. At that point, the universe would consist mostly of black holes, an extremely diffuse radiation. And then even the black holes would eventually disappear. Because black holes aren't perfectly black. Stephen Hawking showed that black holes emit a tiny amount of radiation due to quantum effects near the event horizon. This is known as Hawking radiation. It's incredibly faint, but over immense timescales, it causes black holes to lose mass and slowly evaporate. A black hole with the mass of our sun would take roughly 10.67 years to evaporate completely. A supermassive black hole with 1 billion times the sun's mass would take about 10^100 years. And after around 10^100 years, give or take, the universe enters what's sometimes called the dark era. All stars have burned out. All star formation has ended. Most matter has decayed. All black holes have evaporated. What remains is an unimaginably thin, cold soup of photons and a handful of elementary particles spreading out as space keeps expanding. As the expansion continues, the temperature approaches absolute zero. There is no structure, no complexity, no meaningful change. Just space, expanding forever, colder, emptier, darker. This is what's known as the heat death of the universe. It's the ultimate fate predicted by our current understanding of cosmology and thermodynamics. The universe began in the Big Bang. It has been evolving for 13.8 billion years. It will continue evolving for trillions of years more. But eventually, the processes that create complexity will fade away. The universe will approach a state of maximum entropy, where energy is spread out as evenly as possible and nothing can really happen anymore. It's a bleak idea. But remember, these timescales are so vast that they're almost impossible to truly comprehend. 10 to the power of 100 years is not just a long time. It's an absurd, incomprehensible span of time. For comparison, the current age of the universe is about 1.410 years. Heat death lies on the order of 1090 times farther into the future than everything that has already happened since the Big Bang. That's a one followed by 90 zeros. There is no intuitive way to grasp a number like that. And there's another crucial point to keep in mind. All of these predictions are based on our current understanding of physics and cosmology. History shows us, again and again, that this understanding can change dramatically. Just 100 years ago, we didn't know about dark energy. We didn't know the universe was expanding. We didn't know about quantum mechanics or general relativity. Concepts that now form the foundation of modern physics were completely unknown. So who knows what we might discover in the next 100 years, or the next 1,000 years, that could radically change our predictions about the ultimate fate of the universe. For now, based on what we know, the scale of the universe includes not just space, but time. Immense distances we can observe, probably far more beyond that, possibly infinite. And trillions upon trillions of years stretching into the future as the universe continues to evolve and change in ways we can only partially predict. Let's come back to the present moment. To now. To tonight, as you're experiencing this. You exist in a universe that's 13.8 billion years old, on one planet, orbiting one star in one galaxy. That galaxy is part of a group, which is part of a supercluster, which is part of a vast cosmic web stretching across the observable universe. And beyond what we can observe, there is almost certainly much more. The scale of the universe is not just big, it's beyond big. It's so large that every attempt we make to truly comprehend it falls short. We can do the math, we can write down the numbers, we can build visualizations and scale models, but we can't genuinely feel what it means. Our brains evolved to understand human scales, meters, kilometers, maybe a few thousand kilometers, not light years, not billions of light years, not structures spanning 10 billion light years, not trillions of galaxies, and yet we can still understand it intellectually. We can study it. We can measure it. We can build theories that explain how it works. We can send spacecraft to explore our solar system. We can build telescopes that look billions of light years into space and billions of years back in time. We can map the large-scale structure of the universe. We can calculate its age using the cosmic microwave background. We can detect gravitational waves from black holes colliding billions of light years away. That ability to understand the universe, to comprehend our place in it, even when that place seems impossibly small, is what makes us special. It's what makes Earth special, because as far as we know, Earth is the only place where the universe has developed the ability to understand itself. Think about that. Through us, the universe is looking back at itself. The atoms that make up your body were forged in stars that lived and died billions of years ago. You are literally made of stardust. Those atoms have been drifting through space for eons, cycling through stars, planets, rocks, oceans, air, until they became part of you. A conscious being capable of asking questions about the universe and discovering real answers. That's extraordinary. That's what gives all of this meaning. Despite the overwhelming scale, despite how vast and indifferent the universe may seem, Earth, tiny and insignificant in size, is home. It's where life emerged. It's where consciousness arose. It's where we built telescopes, spacecraft, computers, and laboratories. It's where we uncovered the laws of physics, learned how stars work, and discovered that the universe is expanding. The scale of the universe should humble us. It should remind us how small we are, how brief our time is, how little of the cosmos we can ever reach or even observe. But it should also inspire us, because despite being so small, despite living on a tiny world in a vast and mostly empty universe, we've managed to understand an incredible amount. We've measured the size of the universe. We've traced its history back to the Big Bang. We've predicted aspects of its future. We've discovered planets orbiting other stars. We've detected ripples in spacetime from cataclysmic events billions of light years away. And we've done all of this in just a few hundred years of modern science. Imagine what we might discover in the next few hundred years, or the next few thousand. We might find life on other worlds. We might develop technologies that allow us to travel beyond our solar system. We might solve the mysteries of dark matter and dark energy. We might find a way to unify quantum mechanics and general relativity. We might even figure out how to survive the eventual death of our sun and preserve our civilization for billions of years. Or we might not. We might destroy ourselves before we ever get the chance. We might fail to overcome challenges like climate change, nuclear weapons, or asteroid impacts. We might remain confined to this single planet, this tiny speck in an immense universe, never venturing beyond our immediate cosmic neighborhood. And that's exactly why understanding the scale of the universe matters. It gives us perspective. It reminds us that we're part of something far larger than ourselves, something that's been evolving for 13.8 billion years and will continue for trillions more. It shows us that Earth is precious, not because it's large or cosmically important, but because it's home. It's the only place we have. And as far as we know, it may be the only place in the universe where life exists, where consciousness exists, where anyone is looking up at the stars and wondering about their place in the cosmos. The scale of the universe is overwhelming. It should be. It's meant to overwhelm our intuitions and force us to rethink our place in existence. But that feeling of being overwhelmed shouldn't lead to despair or nihilism. It should lead to wonder. Wonder at how much exists. Wonder at how much we've already managed to understand. And wonder at how much more there is still left to discover. And that is the story we've told tonight. A story that began with Earth and expanded outward through the solar system, the Milky Way, the local group, Laniakea, and far beyond. A story that traced scales from the familiar to the incomprehensible. A story that revealed that almost everything that exists is invisible to us. Dark matter and dark energy that we can measure but cannot see. A story that spans not only space, but time. From the Big Bang, 13.8 billion years ago, to the heat death trillions upon trillions of years in the future. It's a story that shows how rare structure is in the universe, how most of space is empty, how matter is the exception rather than the rule. But it's also a story about us, about how we, living on this tiny world, have somehow managed to comprehend something so vast it should be beyond comprehension, about how we've measured the unmeasurable, mapped the seemingly infinite, and begun to understand the incomprehensible, about how consciousness, curiosity, and the scientific method have allowed us to look out at the cosmos, see it for what it is, and understand our place within it, even when that place feels impossibly small. But before we finish, let's slow down and look at some specific structures in more detail, because concrete examples help make the incomprehensible just a little more graspable. We'll start close to home and work our way outward, adding layers of detail that help anchor what we're talking about. Consider Alpha Centauri, the nearest star system to our sun. It isn't a single star, but a system of three. Alpha Centauri A and Alpha Centauri B form a binary pair, orbiting their common center of mass every 80 years. Proxima Centauri, the closest of the three to us, at about 4.24 light-years away, orbits the pair at a much greater distance. Proxima Centauri is a red dwarf, much smaller and cooler than our sun. It has at least 2 known planets, including one called Proxima b, which orbits within the habitable zone where liquid water could potentially exist on the surface. Even so, the journey to Proxima Centauri at current spacecraft speeds would take tens of thousands of years. Voyager 1, the fastest spacecraft ever to leave the solar system, travels at about 61,000 kilometers per hour relative to the Sun. At that speed, it would take roughly 73,000 years to reach Proxima Centauri. That's longer than recorded human history, longer than agriculture has existed, longer than modern humans have existed as a distinct species. And Proxima Centauri is close. It's literally the nearest star. Most stars in our galactic neighborhood are much farther away. Sirius, the brightest star in Earth's night sky, lies about 8.6 light-years away. Betelgeuse, the red supergiant marking Orion's shoulder, is about 550 light-years distant. When you look at Betelgeuse tonight, you're seeing light that left that star in the 15th century, during the Renaissance, before Columbus sailed to the Americas. The distances between stars in our local region are typical for the Milky Way. In the galactic disk, stars are separated by an average of about 5 light-years. Some are closer, some farther, but 5 light-years is a reasonable average. In the central bulge of the galaxy, where stars are packed much more tightly, separations can drop to 1 or 2 light-years. In the halo, the diffuse outer regions surrounding the galaxy, stars are far more spread out, sometimes separated by tens or even hundreds of light-years. Our Sun orbits the center of the Milky Way at about 828,000 kilometers per hour, completing one full orbit every 225 to 250 million years. We're currently about 26,000 light-years from the galactic center, and that center is a strange, extreme, and violent place. At its heart lies Sagittarius A, a supermassive black hole with a mass about 4 million times that of the Sun. We can't see the black hole directly, no light escapes from it, but we can observe stars orbiting around it. By tracking their motions, astronomers can precisely calculate the black hole's mass. Some of these stars orbit incredibly close. One star, known as S2, completes an orbit in just 16 years. At its closest approach, it comes within about 17 light-hours of the black hole, roughly the distance from the Sun to Uranus. At that point, it's moving at about 3% of the speed of light, fast enough that relativistic effects become measurable. Astronomers have directly observed these effects, confirming predictions made by Einstein's general theory of relativity. The region around Sagittarius AIs is densely packed, with millions of stars crowded into just a few light-years. They orbit at high speeds, occasionally passing near one another in a chaotic, energetic environment. This is nothing like the calm, orderly region where our solar system exists. If Earth were somehow transported there, intense radiation from nearby stars would likely sterilize the planet, and gravitational disturbances from passing stars could disrupt planetary orbits or eject planets entirely. Now, zoom back out and consider the Milky Way as a whole. The galaxy has several distinct components. There's the thin disk, about 1,000 light-years thick, where most of the stars and all the spiral arms reside. This is where our Sun is located. Surrounding that is the thick disk, extending about 3,000 light-years above and below the thin disk. The thick disk contains older stars with different chemical compositions, suggesting they formed earlier in the galaxy's history. At the center lies the bulge, a roughly spherical concentration of stars extending about 10,000 light-years from the core. The bulge contains mostly older stars. Beyond that is the halo, a vast, diffuse spherical region stretching perhaps 100,000 down to 200,000 light-years from the center. The halo contains ancient stars, globular clusters, tight spherical groupings of hundreds of thousands of stars, and large amounts of dark matter. The spiral arms themselves aren't solid structures. They're density waves, regions where gas and stars are temporarily compressed as they orbit the galactic center. A useful analogy is a traffic jam on a highway. Cars enter the jam, slow down, then exit and speed up again. The traffic jam persists even though individual cars are constantly moving through it. Spiral arms work the same way. Stars and gas clouds pass through them, but the arms remain as long-lived patterns. The Milky Way has 4 major spiral arms and several smaller ones. Our Sun currently sits between 2 major arms, in a region often called the Orion Spur, or local arm. We've been here for millions of years, and will remain here for millions more. As the Sun completes each 225 million year orbit, it will drift into a major arm, and then back out into another quieter region. Now let's look at our neighbors in the local group. Andromeda, the largest member, lies about 2.5 million light-years away, and is approaching us at roughly 110 kilometers per second. In about 4 billion years, Andromeda and the Milky Way will collide and merge, forming a new elliptical galaxy, often nicknamed Milkomeda or Milkdromeda. As the merger unfolds, the night sky will change dramatically. Andromeda will grow larger and brighter, eventually dominating the sky with its spiral structure clearly visible. Gas clouds will collide and compress, triggering bursts of star formation. New bright stars will light up the merged galaxy. But individual stars will almost certainly not collide. The distances between stars are simply too great. It's like throwing two handfuls of sand at each other. Most grains pass by without touching. The same is true for stars. The real effects come from gravity, reshaping orbits and redistributing stars around the new galaxy center. The Triangulum galaxy, the third largest member of the local group, lies about 2.7 million light-years away. It contains around 40 billion stars and is likely gravitationally bound to Andromeda. During the Milky Way-Andromeda merger, Triangulum may also be drawn in, adding further complexity. The local group also contains dozens of dwarf galaxies. These small galaxies, with millions to billions of stars, orbit the larger members. The Large and Small Magellanic Clouds, visible from the southern hemisphere as faint patches in the sky, are irregular dwarf galaxies orbiting the Milky Way. The Large Magellanic Cloud lies about 160,000 light-years away and contains roughly 20 billion stars. The Small Magellanic Cloud is about 200,000 light-years away and contains around 3 billion stars. These dwarf galaxies are slowly being torn apart by the Milky Way's gravity. Long streams of stars and gas trail behind them, evidence of ongoing tidal disruption. Over hundreds of millions of years, the Magellanic Clouds will be absorbed into the Milky Way, their stars blending with ours. This is how large galaxies grow, by consuming smaller ones. The Milky Way has absorbed many dwarf galaxies in the past, and it will absorb more in the future. Now let's expand our view even further to what was once called the Virgo supercluster, but is now more accurately known as Laniakea. Laniakea means immeasurable heaven in Hawaiian, and it's an entirely fitting name. This supercluster contains roughly 100,000 galaxies spread across about 520 million light-years. That's more than 5,000 times the diameter of the Milky Way. To put that into perspective, if the Milky Way were the size of a dime, about 18 millimeters across, then Laniakea would span roughly 94 meters, about the length of a football field. But Laniakea isn't a neat, spherical structure. It's more like a flattened sheet, threaded with filaments extending outward in multiple directions. The galaxies within it are arranged in a complex cosmic web, clustering along filaments and leaving vast voids in between. The entire structure is in motion, with galaxies flowing through space under the influence of gravity, drawn toward regions of higher mass density. At the center of this flow lies something called the Great Attractor. The Great Attractor is a region of space about 250 million light-years away, where the gravitational pull is unusually strong. It's drawing thousands of galaxies toward it, including the Milky Way itself. We are moving in that direction at about 600 kilometers per second. But even the Great Attractor isn't the largest influence in our cosmic neighborhood. Beyond it lies an even more massive concentration of matter, known as the Shapley concentration, or the Shapley supercluster, located about 650 million light-years away. This immense structure contains more than 8,000 galaxies and represents one of the largest concentrations of matter in the nearby universe. These enormous structures, superclusters, attractors, filaments, and walls tell us something fundamental about the universe. Matter is not distributed randomly. It's organized into structure upon structure across many different scales: planets, stars, galaxies, clusters, superclusters, filaments, and walls. And all of this structure exists because of gravity. Gravity pulled matter together from an initially almost uniform universe into the intricate cosmic web we observe today. In the early universe, about 380,000 years after the Big Bang, matter was distributed nearly evenly. The differences in density were tiny, about 1 part in 100,000. But those tiny differences were enough. Regions that were slightly denser exerted slightly stronger gravitational pull, drawing in more matter and becoming denser still. This runaway process, known as gravitational instability, is what built the large-scale structure of the universe. We can actually see evidence of this in the cosmic microwave background radiation, the afterglow of the Big Bang. When astronomers map the CMB across the sky, they see minute temperature variations. Hotter regions correspond to slightly overdense areas. Cooler regions correspond to slightly underdense ones. Those tiny fluctuations are the seeds from which all galaxies, clusters, superclusters, and cosmic walls eventually grew. Now let's talk about some of the largest structures in the observable universe. The Sloan Great Wall, which we mentioned earlier, stretches about 1.37 billion light-years across. It's a colossal filament of galaxies, a cosmic thread spanning more than 1% of the diameter of the observable universe. The galaxies within it are not all at the same distance from us. The structure has depth. It's more like a vast sheet or membrane of galaxies, several hundred million light-years thick, but more than 1 billion light-years long. Another massive structure is the CFA2 Great Wall, discovered in 1989. It's about 500 million light-years long and roughly 200 million light-years wide, containing tens of thousands of galaxies. The Virgo supercluster, including the Milky Way, is actually part of this enormous structure. We are living inside one of the largest cosmic features visible in the nearby universe. Even larger is the Hercules Corona Borealis Great Wall. If it truly is a single coherent structure, it stretches roughly 10 billion light-years across, more than 10% of the diameter of the observable universe. It was discovered by studying the distribution of gamma-ray bursts, which are among the most powerful explosions in the universe, thought to occur when massive stars collapse. Gamma-ray bursts are so bright they can be detected across vast cosmic distances, making them useful probes of large-scale structure. The existence of the Hercules Corona Borealis Great Wall is controversial. Some astronomers argue that it may not be a single structure at all, but rather a chance alignment of smaller ones. But if it is real, it poses a serious challenge to cosmology. According to the cosmological principle, which states that the universe should look roughly the same in all directions on sufficiently large scales, structures larger than about 1.2 billion light-years shouldn't exist. This structure would be nearly 8 times larger than that theoretical limit. Its existence would imply either that the cosmological principle is incomplete, or that our understanding of how cosmic structures form is still missing something fundamental. Between these massive walls and filaments lie the voids. The Botas Void, discovered in 1981, is a roughly spherical region, about 330 million light-years across, that contains very few galaxies. In a volume that size, you'd normally expect around 2,000 galaxies. The Botas Void contains only about 60, roughly 97% fewer than average. It's not completely empty, but it's far emptier than most regions of space. If you were placed at the center of the Botas Void, the nearest significant concentration of galaxies would be more than 150 million light-years away in every direction. The night sky would be almost entirely dark. No bright Milky Way band. No nearby galaxies visible to the naked eye. Just darkness, and the faint glow of the cosmic microwave background, the last lingering light from the Big Bang. There are many other enormous voids scattered throughout the universe. The giant void in Cain's Venatici spans about 1.3 billion light-years. The CMB cold spot, a particularly large and unusually cold region in the cosmic microwave background, may be caused by a supervoid nearly 1.8 billion light-years across. These structures push the limits of what our models predict and force us to refine our understanding of how the universe evolved. When astronomers map the positions of galaxies in 3 dimensions, a clear pattern emerges. Galaxies trace out a cosmic web. Long filaments stretch across hundreds of millions or billions of light-years, connecting dense nodes where galaxy clusters form. Between them lie vast voids, enormous bubbles of near emptiness. The pattern resembles foam or a sponge, with galaxies forming thin surfaces around bubbles of empty space. This is not random. Computer simulations that start with the tiny density variations seen in the early universe and allow gravity to act over 13.8 billion years naturally produce filaments, nodes, and voids that look strikingly similar to what we observe. These simulations also reveal something crucial. Most of the matter in the universe isn't inside galaxies at all. It resides in the filaments, in the form of diffuse gas and dark matter. Galaxies are just the bright markers, like cities along a highway. The highway itself, made of dark matter and gas, is what defines the structure. The cities are simply where matter becomes dense and luminous enough for us to see. When we look at maps of the cosmic web, we're seeing only a small fraction of what's really there. The galaxies we observe contain only about 10% of ordinary matter. The remaining 90% exists as diffuse gas in the filaments, too hot and too spread out to form stars. And then there's dark matter, which outweighs ordinary matter by roughly a factor of 5. Dark matter forms its own invisible web, and ordinary matter flows along the gravitational landscape it creates. Now let's talk about numbers that truly defy comprehension. The Hubble Deep Field and Ultra Deep Field images revealed that even regions of sky that appear empty contain thousands of galaxies when observed long enough. When astronomers add up all the stars in all those galaxies, they arrive at a number on the order of 200 billion trillion stars. That's a 2 followed by 23 zeros. If you tried to count them at a rate of 1 star per second, without sleeping, without stopping, it would take about 6 quadrillion years. For comparison, the universe itself is only 13.8 billion years old. You'd need to count for roughly 435,000 times longer than the universe has existed just to finish counting the stars. And each of those stars likely has planets. Current exoplanet surveys suggest there may be more planets than stars, perhaps 1.5 to 2 planets per star on average. That means there are at least 300 billion trillion planets in the observable universe. Some are rocky worlds like Earth. Some are gas giants like Jupiter. Some are icy worlds like Neptune. And many orbit within the habitable zones of their stars. Among all those planets, there must be billions, perhaps trillions, that are broadly Earth-like. How many of them harbor life? We don't know. We have only one example: Earth. We don't yet know whether life is common or extraordinarily rare. We don't know whether the conditions that gave rise to life on Earth are easy to replicate or incredibly unlikely. But given the sheer number of planets, it seems improbable that Earth is truly unique. Even if only 1 in a billion Earth-like planets develops life, that would still mean hundreds of billions of life-bearing worlds in the observable universe. And how many of those develop intelligent life? Again, we don't know. On Earth, simple life appeared relatively quickly, within the first billion years after the planet became habitable. What happened after that may be common, or it may be vanishingly rare. For now, that question remains one of the greatest open mysteries in all of science. Because while simple life showed up relatively fast, complex multicellular life took far longer, roughly 3 billion years after the first simple organisms appeared. And intelligent, technological civilization, that's basically a blink. It's emerged only within the last few 100,000 years, a microscopic slice of Earth's total history. So maybe intelligence is rare, something that requires a long chain of unlikely events, each one a bottleneck. Or maybe it's common, something that becomes inevitable once life gets going. We simply don't know. That uncertainty is captured in what's called the Drake equation, formulated by astronomer Frank Drake in 1961. It attempts to estimate the number of detectable civilizations in our galaxy by multiplying together a series of factors: the rate of star formation, the fraction of stars with planets, the number of habitable worlds per star, the fraction that develop life, the fraction that develop intelligence, the fraction that develop technology, and the length of time they remain detectable. And depending on what values you plug in, the Drake equation gives wildly different answers. Optimistic assumptions can produce thousands, Shenji millions, of civilizations in the Milky Way alone. Pessimistic assumptions can drop that number to 1, us. And then there's the awkward, haunting follow-up problem. We haven't heard anything. Despite decades of searching with radio telescopes, we've detected no clear signal from another civilization. That uncomfortable mismatch between "it should be crowded" and "it sounds silent" is called the Fermi Paradox, named after physicist Enrico Fermi, who supposedly asked, during a lunch conversation in 1950, "Where is everybody?" If intelligent civilizations are common, why don't we see evidence of them? There are many possible answers. Maybe civilizations are extremely rare. Maybe they're common, but short-lived, destroying themselves before spreading very far. Maybe they exist, but they don't use radio waves. Maybe they're out there, but they're too far away for us to detect. Maybe they're deliberately hiding. Maybe we're looking in the wrong way, or for the wrong kind of signal. We don't know. But whether we're alone or not, the scale of the universe forces the same reality on everyone. The distances between stars are enormous. Interstellar travel, if it's possible at all, would be brutally hard. Even traveling at a significant fraction of the speed of light, you're still talking about journeys that take centuries or millennia. And communication is trapped by the speed limit of the universe, light. If you sent a message to Proxima Centauri today, it would take 4.24 years to arrive. And even if someone replied instantly, it would take another 4.24 years to get back. That's nearly a decade for a single hello. For more distant stars, the delays become absurd. So even if the Milky Way were teeming with civilizations, they could still be isolated from each other by sheer scale. They can't easily travel between stars. They can communicate, but with delays that make real-time conversation impossible. In a practical sense, each civilization is alone, staring out at a universe full of worlds, but unable to truly reach them. Now let's go deeper into dark matter. We've established that it exists. The gravitational evidence is overwhelming. But what exactly is it? The leading candidate for decades has been a class of hypothetical particles called WIMPs, weakly interacting massive particles. These would be particles with mass that interact through gravity and possibly the weak nuclear force, but not through electromagnetism. That means they wouldn't emit, absorb, or reflect light, making them invisible to telescopes. They would pass through ordinary matter almost without interacting, which helps explain why we haven't detected them yet. But despite decades of searching, nothing definitive has shown up, and that leaves the door open to other candidates. Axions are another possibility, hypothetical particles far lighter than WIMPs, but potentially present in enormous numbers. Primordial black holes, formed in the early universe rather than from collapsing stars, are another idea. Or dark matter could be something completely unexpected, some new particle, or new physics we haven't even imagined yet. Whatever it is, dark matter is essential to the structure of the universe. Without it, galaxies likely wouldn't have formed the way they did. Ordinary matter alone didn't have enough gravitational pull to clump together quickly enough in the early universe. Dark matter collapsed first, forming deep gravitational wells, and then ordinary matter fell into those wells. In that sense, galaxies are built on an invisible foundation. Dark matter forms halos around galaxies that extend far beyond their visible stars. The Milky Way's dark matter halo likely stretches 200,000 light-years or more from the galactic center, well beyond the bright disk of stars. That halo contains several times more mass than all the stars and gas in the galaxy combined. We're moving through it right now. As Earth orbits the Sun, and as the Sun orbits the galactic center, all of it is traveling through a vast ocean of dark matter. And then there's dark energy. Dark energy is even more mysterious than dark matter. It makes up about 68% of the universe's total energy density, more than dark matter and ordinary matter combined. It's responsible for the accelerating expansion of the universe. Unlike gravity, which pulls things together, dark energy pushes space apart. And the more space there is, the more dark energy there appears to be. So the repulsive effect grows stronger as the universe expands. The simplest explanation is that dark energy is a property of space itself, often described as the cosmological constant, or vacuum energy. And here's where the story gets weird. According to quantum field theory, even empty space isn't truly empty. It's filled with virtual particles constantly popping into and out of existence. Those fluctuations carry energy, and that vacuum energy could be what we observe as dark energy. But when physicists calculate the expected energy of the quantum vacuum, they get a value that's about 1 to 120 times larger than what we observe. That's a 1 followed by 120 zeros. It's one of the largest, most embarrassing mismatches between theory and observation in all of physics. Either the calculation is wrong in a profound way, or there's some mechanism that cancels out almost all of the vacuum energy, leaving only a tiny remainder. And nobody knows which. What we do know is that dark energy is accelerating the expansion of the universe. Distant galaxies are moving away faster and faster. And eventually, billions of years from now, galaxies outside our local group will recede so fast that their light will be stretched, redshifted, and diluted into invisibility. One by one, they'll vanish from view, leaving only the galaxies bound to us by gravity. The universe will appear to empty out. Only a few dozen galaxies will remain visible. Everything else will fade into darkness. This has profound implications for the far future. Any civilizations that arise trillions of years from now will see a universe completely different from ours. They may see only their local group of galaxies and no evidence of anything beyond. They will not observe the cosmic microwave background. It will be so redshifted and diluted that it will be essentially undetectable. They will not see distant galaxies. They will not map the large-scale structure. They may conclude that their local group is the entire universe. We are living in a special cosmological era. We can see the cosmic microwave background. We can see distant galaxies and measure their recession. We can map the cosmic web. We have direct evidence of the Big Bang and the expansion of space. Future civilizations may not have any of that. They might be unable to reconstruct the full history of the cosmos, not because they're less intelligent, but because the evidence will be gone. And that raises a deeper question. Are there cosmic events that happened in the past that we can never know about because the evidence has already faded away? Are there aspects of the early universe, perhaps even something before the Big Bang, that we can't observe because there is no trace left? We know the Big Bang happened because we can see the CMB and we observe expansion. But what if there were events before the Big Bang that left no observable footprint? What if our universe is one cycle in a repeating series? Expansion, contraction, expansion again. But the evidence of previous cycles was erased. These questions touch the edge of what science can do. Science is built on observation and evidence. If something leaves no observable trace, it can't be studied scientifically. We can speculate. We can build mathematical models. But without evidence, we can't confirm or rule them out. So there may be aspects of reality that are fundamentally beyond our ability to observe. And that brings us to the multiverse hypothesis, the idea that our universe might be just one of many. In some versions of inflation theory, our universe is one bubble in an eternally inflating background. New universes are constantly forming, each potentially with different physical laws and constants. We live inside one bubble, but there may be countless others forever beyond our ability to observe or interact with. In some interpretations of quantum mechanics, every measurement splits reality into branches where all possible outcomes occur. You experience one branch. Other versions of you exist in other branches, seeing different outcomes. Those parallel universes would be real, but fundamentally inaccessible to each other. So are these ideas science or philosophy? It's complicated. Some of the theories that imply a multiverse do make testable predictions. Inflation theory, for instance, predicts certain patterns in the cosmic microwave background, and many of those predictions have been confirmed. But the multiverse itself, the other universes, is, by definition, unobservable. So the framework may be scientific, while the implied other universes may be permanently beyond experimental reach. And this loops right back to the scale of the universe. If the multiverse idea is correct, then even an infinite universe might be just one tiny piece of reality. There could be countless other universes, each potentially infinite in its own way, each with its own laws and history. At that point, scale stops being merely large and becomes literally incomprehensible. An infinite universe is already beyond human intuition. An infinite collection of infinite universes is even more so. Mathematicians have language for these ideas. Transfinite numbers, different sizes of infinity. But those are abstractions. Whether they correspond to physical reality is another question entirely. And yet, here we are, on Earth. A planet 12,742 kilometers wide, orbiting one star, in one galaxy, in a universe that might be infinite, in a multiverse that might be even more infinite. The scale is overwhelming, but we exist, we're conscious, we're asking these questions. That alone is remarkable. Now think about what had to happen for you to be here. The universe had to begin with the Big Bang. It had to expand and cool. The first stars had to form and manufacture heavy elements through nuclear fusion. Those stars had to die, many of them in supernova explosions, scattering those heavy elements back into space. New generations of stars, including our sun, had to form from clouds already enriched by that stellar debris. Planets had to form around our sun. Earth had to form at exactly the right distance, in the habitable zone where liquid water could exist. It had to have the right mass, massive enough to hold an atmosphere, but not so massive that it became a gas giant. It needed water, carbon, and the full inventory of elements life depends on. Life had to begin, which required the right chemistry and a steady source of energy. Life had to survive for billions of years through asteroid impacts, mass extinctions, volcanic winters, ice ages, and catastrophes that could have erased it entirely. Complex life had to evolve, which required stable environmental conditions over immense stretches of time. Intelligence had to evolve, which required the right evolutionary pressures. Civilization had to emerge, which required cooperation, language, culture, and technology. And then you had to be born, the product of an unbroken chain of ancestors stretching back billions of years, every single one of whom survived long enough to reproduce. The odds of any particular individual existing are astronomically small. If even one of millions of events across 13.8 billion years had unfolded differently, you wouldn't exist. But here you are, and the fact that you exist means something else. You can understand the universe, at least partially. You can look up at the night sky and grasp that those points of light are suns like ours, separated by light years of space. You can understand that the universe is far larger than intuition suggests. You can comprehend, at least intellectually, that you are part of something immense. That ability, the ability to understand the universe while being an infinitesimally small part of it, is what makes us special. Consciousness is rare in the universe, possibly unbelievably rare. Most of the universe is empty space, nearly void of matter. Most matter exists as stars or diffuse gas, not as living organisms. Most planets are probably lifeless. Even on Earth, most of the planet's history was dominated by simple, single-celled life. Complex multicellular life, with specialized tissues and organs, appeared only within the last billion years or so. And intelligent life capable of building telescopes, launching spacecraft, and understanding cosmology has existed for only a tiny fraction of that already tiny slice. We don't know if we're alone, but we do know that consciousness is exceptional, rare, precious. And the fact that consciousness exists at all, that the universe produced beings capable of understanding it, is one of the most astonishing facts about reality. So yes, the universe is vast. The true scale of the universe is beyond anything we can fully grasp. But that vastness makes our existence more remarkable, not less. We're small, but we're not insignificant. We're part of the universe becoming aware of itself. We are the universe looking back and asking questions about its own nature. And in a cosmos where most of space is empty and most matter is lifeless, that is extraordinary. But let's go deeper into specific aspects of cosmic scale that help us understand just how strange and magnificent this universe really is. Let's talk about cosmic time, because the scale of time is every bit as staggering as the scale of space. The universe began 13.8 billion years ago with the Big Bang. In the first fraction of a second after the Big Bang, it went through an episode of exponential expansion called inflation. In less than a trillionth of a trillionth of a trillionth of a second, the universe expanded from something smaller than an atom to something roughly the size of a grapefruit. That is an expansion factor of about 100 million trillion. Nothing in everyday experience comes remotely close to that kind of growth rate. After inflation ended, the universe continued expanding, but at a far more moderate pace. For the first 380,000 years, the universe was a hot, dense plasma of particles and radiation. It was opaque, like being inside a glowing fog. Photons couldn't travel far before being scattered by free electrons. Then, about 380,000 years after the Big Bang, the universe cooled enough for electrons and protons to combine into neutral hydrogen atoms. This moment is called recombination. Once recombination occurred, photons were finally able to travel freely. The universe became transparent. And those photons are still traveling through space today. We detect them as the cosmic microwave background radiation, a faint, nearly uniform glow coming from every direction in the sky. The CMB has a temperature of about 2.7 Kelvin, just a few degrees above absolute zero. It has been cooled by the expansion of the universe. When those photons were released, the universe was around 3,000 Kelvin, hot enough to glow like a red heating element. But 8 billion years of expansion has stretched their wavelengths, redshifting them from visible light into microwaves. The CMB is the oldest light we can see. When we observe it, we're looking back to when the universe was only 380,000 years old. It's like looking at a photograph of someone taken as a newborn, except that person is now 80 years old. We're seeing the universe in its infancy. After recombination, the universe entered what's called the Dark Ages. There were no stars yet, no galaxies, just hydrogen and helium gas slowly clumping under gravity. The Dark Ages lasted for hundreds of millions of years. Then, around 200 million years after the Big Bang, the first stars began to form. These were massive stars, some of them hundreds of times more massive than the Sun, burning hot and bright. They lived fast and died young, surviving only a few million years before exploding as supernovae. Those explosions created the first heavy elements heavier than hydrogen and helium. A few 100 million years after the first stars, the first galaxies began to form as gravity pulled gas and dark matter into larger structures. These early galaxies were small, chaotic, and irregular, nothing like the majestic spiral galaxies we see today. Over billions of years, those primitive galaxies merged and grew, gradually building the large galaxies we now observe in the modern universe. Our Sun formed about 4.6 billion years ago, roughly 9 billion years after the Big Bang. That means the universe was already about 2/3 of its current age when our solar system formed. Many generations of stars had already lived and died, creating the heavy elements that make up Earth and everything on it. The iron in your blood, the calcium in your bones, the oxygen you breathe. All of it was forged in stars that exploded before our solar system ever existed. Earth formed shortly after the Sun, and life on Earth appeared relatively quickly, within the first billion years. That means life has existed here for about 3.8 billion years, roughly a quarter of the age of the universe. For most of that time, life remained simple and single-celled. Complex multicellular life only appeared about 600 million years ago, just 4% of Earth's history, or about 1.3% of the universe's history. Humans appeared about 300,000 years ago. That's about 0.08% of Earth's history, or about 0.02% of the universe's history. Written civilization has existed for about 5,000 years, around 0.011% of Earth's history, or about 0.6% of the universe's history. Modern science, the systematic study of nature through observation and experiment, has existed for only about 500 years. That is a microscopic sliver, around 0.01% of Earth's history, and about 0.036% of the universe's history. Think about that. We've had the scientific method, the disciplined, self-correcting way of studying reality, for only about 0.36% of the universe's lifetime. And in that almost non-existent slice of time, we figured out the age of the universe, the size of the observable universe, the nature of stars and galaxies, the structure of atoms, the evolution of life, and countless other deep truths about reality. That is remarkable. It suggests that intelligence, once it emerges, can make astonishingly rapid progress in understanding the cosmos. But it also reveals how fragile this knowledge is. If humanity vanished tomorrow, nearly all of it would be lost. Books would rot, computers would fail, buildings would crumble. In a few million years, there would be almost no trace we were ever here. And any future intelligent species that might evolve on Earth would have to rediscover everything from scratch. They'd need to reinvent agriculture, reinvent writing, rediscover mathematics, rebuild science. It could take thousands of years to reach our current level of understanding, if they ever did at all. That's one reason some people argue for making humanity a multi-planet species. If we spread beyond Earth, then the loss of one planet wouldn't mean the loss of everything. Our knowledge, and our civilization, would be distributed across multiple worlds, making it far harder to erase completely. But for now, all of human knowledge, our art, Our literature, our science, our memories exists only here, on this one small planet. So let's talk about the future of astronomical observation and how our understanding of the universe's scale continues to evolve. For most of human history, we observed the universe with nothing but our naked eyes. Under perfect conditions, a human could see about 6,000 stars. Beyond that, there was the Milky Way stretching faintly across the sky, a handful of wandering planets, the moon, and occasionally a comet or a meteor. That was it. That was the entire observable universe for thousands of years. Then, in the early 1600s, the telescope was invented. Suddenly, the universe expanded. Not physically, but perceptually. Galileo turned a telescope toward the sky and saw moons orbiting Jupiter, phases of Venus, mountains and craters on the moon, and countless stars invisible to the naked eye. The cosmos instantly became larger and more complex than anyone had imagined. Instead of thousands of stars, there were millions. Instead of vague smudges in the sky, there were objects that demanded explanation. Over the next few centuries, telescopes grew larger and more precise. And in the 1920s, Edwin Hubble used the 100-inch telescope at Mount Wilson Observatory to make a discovery that fundamentally changed our understanding of reality. He showed that some of those faint smudges were not clouds or nearby objects, but entire galaxies, separate island universes far beyond the Milky Way. He also discovered that these galaxies were moving away from us, with more distant galaxies receding faster. This was the first evidence that the universe is expanding. In the 1960s, astronomers made another revolutionary discovery: the cosmic microwave background radiation, the faint afterglow of the Big Bang. This provided powerful confirmation that the universe had a beginning and has been expanding and cooling for billions of years. It also allowed scientists to measure the universe's age and determine the relative amounts of matter and energy it contains. Then came the Hubble Space Telescope in 1990. By placing a telescope above Earth's atmosphere, above the turbulence, distortion, and absorption of air, Hubble could see fainter and more distant objects than any ground-based telescope before it. The Hubble Deep Field images, beginning in 1995, revealed something astonishing. In tiny patches of sky that appeared empty, there were thousands of galaxies. These observations suggested that the observable universe contains far more galaxies than previously believed, leading to the current estimate of roughly 2 trillion galaxies. More recently, the James Webb Space Telescope, launched in 2021, has pushed these limits even further. Webb observes primarily in infrared light, which can pass through cosmic dust and capture light from extremely distant galaxies whose wavelengths have been stretched by the expansion of space. Webb has already observed galaxies that formed less than 400 million years after the Big Bang, giving us an unprecedented view of the universe's earliest epochs. And this progress is far from over. Future observatories will continue to expand our cosmic perspective. The extremely large telescope, currently under construction in Chile, will have a mirror 39 meters across, about 4 times larger than today's largest ground-based telescopes. It will be capable of directly imaging exoplanets and analyzing their atmospheres, potentially detecting signs of life. The Nancy Grace Roman Space Telescope, planned for launch in the mid-2020s, will have a field of view about 100 times larger than Hubble's, allowing it to survey enormous regions of space and catalog billions of galaxies. These instruments will help us map the universe in finer detail than ever before. We'll trace how cosmic structures evolved over time. We may observe the first generations of stars. We may uncover clues about dark matter, dark energy, or primordial gravitational waves left over from inflation. But there are limits, fundamental limits, to what we can ever observe. We can never see beyond the cosmic horizon. The boundary defined by the maximum distance light could have traveled since the Big Bang. Anything beyond that distance is forever invisible to us. And as the universe continues to expand and accelerate, that horizon effectively shrinks. Distant galaxies are being carried away by the expansion of space faster than light can reach us, causing them to fade from view one by one. In the far future, billions of years from now, observers living in our local group of galaxies will see a very different universe. They'll see only the Milky Way, Andromeda, and a few dozen smaller galaxies, all gravitationally bound together. Everything else will have disappeared beyond the horizon, redshifted into invisibility. The cosmic microwave background will be stretched and diluted until it's undetectable. Future astronomers might see no evidence of the Big Bang, no evidence of expansion. They might reasonably conclude that their local group is the entire universe. This means we are living in a special time. Cosmologically speaking, we can see the cosmic microwave background. We can observe billions of galaxies. We can map the large-scale structure of the universe and reconstruct its history. This window will not remain open forever. Eventually, the evidence will fade, and future civilizations may be unable to piece together the full story of the cosmos. Now let's consider one more aspect of cosmic scale: infinity. What does infinite actually mean? An infinite universe would have no edge, no center, no boundary. It would extend endlessly in all directions. No matter how far you traveled, you would never reach an edge, because there is no edge. And in an infinite universe, something strange follows. If there's a finite probability for any particular arrangement of matter, then every possible arrangement must exist somewhere. That means infinitely many Earths, infinitely many versions of you, some identical, others differing in small ways, wearing a different shirt today, others differing in profound ways, making entirely different life choices. This isn't science fiction. It's a logical consequence of infinity. These copies would be unimaginably far away, far beyond the observable universe. You could never reach them or communicate with them, but in principle, they would exist somewhere in the endless expanse of space. This is one reason many physicists are uneasy with the idea of an infinite universe. It leads to implications that feel philosophical, even unsettling. And yet, observations suggest that the universe is either infinite or extremely close to infinite. Measurements indicate that space is flat, Euclidean, extending without curvature, rather than closing back on itself like the surface of a sphere. Infinity itself has layers. Mathematicians have shown that some infinities are larger than others. The counting numbers, 1, 2, 3, and so on, form an infinite set. But the numbers between 0 and 1 form a larger infinity, containing every possible decimal. Georg Cantor demonstrated this in the 19th century, revealing that infinity is not a single concept, but a hierarchy. If the multiverse exists, if there are infinitely many universes, each possibly infinite, does that represent a larger infinity still? These questions blur the line between physics, mathematics, and philosophy. They may one day have answers, or they may forever lie beyond our reach. Now bring all of this back to something immediate. You're sitting somewhere on Earth right now, maybe in a room, maybe outdoors. Around you are familiar objects: walls, furniture, trees, buildings. You can see tens or hundreds of meters in any direction. That's the human scale. But zoom out. Your room is enormous compared to an atom, but microscopic compared to Earth. Earth is vast compared to you, but tiny compared to the Sun. The Sun is immense compared to Earth, yet insignificant compared to the Milky Way. And the Milky Way, with its hundreds of billions of stars, is just a faint thread in a universe so vast that even our best descriptions fall short. And yet, here you are, aware, curious, asking questions. In a universe defined by emptiness and scale, that may be the most extraordinary thing of all. The Sun is enormous compared to Earth, but tiny compared to the distance to the nearest star. And the scales continue like this, one after another, each dwarfing the last, until we reach structures so immense that describing them meaningfully becomes almost impossible. At every step, the scale increases by factors of thousands, millions, or billions. At every step, what once seemed vast becomes small. The room you're in is enormous compared to an atom, yet tiny compared to Earth. Earth is enormous compared to a human, yet tiny compared to the Sun. The Sun is enormous compared to Earth, yet tiny compared to the distances between stars. And this pattern continues, scale after scale, until we reach the observable universe, a structure so large that our language and intuition begin to break down. And yet, something remarkable remains true at every level. The same physical laws apply everywhere. Gravity behaves the same way, whether you're talking about an apple falling from a tree or galaxies clustering into superclusters. Electromagnetism works the same, whether it's a magnet sticking to a refrigerator or light traveling from a distant quasar. The laws of thermodynamics, quantum mechanics, and nuclear physics operate universally, at every scale, everywhere in the universe as far as we can tell. This universality is one of the deepest discoveries in all of science. The universe is comprehensible because it follows rules, and those rules are the same everywhere. A hydrogen atom on Earth is identical to a hydrogen atom in a galaxy billions of light years away. The speed of light is the same here as it is at the edge of the observable universe. This is why we can understand distant objects by studying nearby ones. We learn about stars by studying the sun. We learn about galaxies by studying the Milky Way. We learn about the universe by studying the small region of it we can directly observe. But mysteries remain. Dark matter and dark energy are the most obvious examples, but they're not the only ones. We still don't know how to reconcile quantum mechanics and general relativity, the two great pillars of modern physics. Each works extraordinarily well in its own domain, yet they give conflicting predictions at extreme conditions, such as inside black holes or during the earliest moments of the Big Bang. We need a theory of quantum gravity, a unified framework that includes both. Despite decades of effort, we don't have one. We don't understand consciousness, how physical matter gives rise to subjective experience. We don't know whether consciousness is rare or common in the universe. We don't know whether artificial intelligence could become conscious, or whether consciousness requires biological processes. If the multiverse exists, we don't know whether the laws of physics are the same everywhere. We don't know why the fundamental constants of nature have the values they do. Why is the speed of light what it is? Why does the electron have its particular mass? Some versions of the multiverse hypothesis suggest that these constants vary from universe to universe, and that we observe the values we do simply because they allow atoms, stars, planets, and life to exist. These are profound questions, and we don't yet have answers. But the fact that we can ask these questions, that we can frame them in ways that might someday be answerable, is extraordinary in itself. Just a few hundred years ago, we didn't even know other galaxies existed. We thought the Milky Way was the entire universe. Today, we're discussing multiverses and different sizes of infinity. Our understanding has grown enormously, and there's every reason to believe it will continue to grow. So the true scale of the universe isn't just about size. It's about complexity. It's about structure at many levels. It's about laws that apply everywhere. It's about mysteries still waiting to be solved. And above all, it's about the astonishing fact that tiny beings on a tiny planet can comprehend any of this at all. When you look up at the night sky, you're looking across space and back in time. The light from nearby stars has been traveling for years, or decades to reach you. The light from distant galaxies has been traveling for millions or billions of years. You're seeing those objects not as they are now, but as they were when that light began its journey. The night sky is a window into the past. Every photon that enters your eye, every particle of light that strikes your retina, has traveled across vast stretches of space just to reach you at this moment. That photon may have been emitted by a star millions of years ago. It crossed the emptiness of space, avoided every obstacle, and arrived at Earth at precisely the moment you happened to be looking up. The odds of that are infinitesimally small. And yet it happened. That's part of the wonder of the universe. We are connected to the cosmos in profound ways. The atoms in our bodies were forged in stars. The light we see comes from stars. The energy that powers our civilization ultimately comes from the sun, whether directly through solar power or indirectly through fossil fuels, which are ancient sunlight stored in chemical form. We are not separate from the universe. We are made of the same material, governed by the same laws, part of the same story that began 13.8 billion years ago with the Big Bang. Understanding the scale of the universe changes how we see ourselves. It humbles us, showing how small we are. But it also elevates us, showing that we are capable of understanding something vastly larger than ourselves. We are the universe's way of knowing itself, of reflecting on its own existence. That is extraordinary. And perhaps most importantly, understanding the scale of the universe gives us perspective on our own lives, on our worries, our conflicts, our ambitions. These things matter deeply to us and to those around us. But on cosmic scales, they are fleeting. The universe doesn't care about our arguments or our status or our anxieties. It will continue regardless, and that isn't depressing. It's liberating. It means we are free to focus on what truly matters: our relationships, our experiences, our growth as individuals and as a species. We are free to create meaning, to explore, to learn, to wonder. The universe provides the stage. We create the story. So when you think about the scale of the universe, don't let it overwhelm you. Don't let it make you feel insignificant. Let it inspire you. Let it remind you that you're part of something vast, ancient, and beautiful. Let it push you to learn more, to explore more, to understand more. Because every fact we uncover about the universe is a victory of understanding over ignorance, of light over darkness. And in a universe that is mostly empty and mostly dark, every spark of understanding matters. The universe is vast, but it is not unknowable. It is immense, but it is comprehensible. It is ancient, but we are uncovering its history. It is complex, but we are learning how it works. And that's what makes the scale of the universe not just a fact to remember, but a truth to celebrate. We live in an extraordinary cosmos, and we have the rare privilege of being able to understand it. Thank you for taking this long journey across space, time, and scale. The true scale of the universe may be beyond what any of us can fully grasp, but the attempt to grasp it, the effort to understand, is what makes us human. And when you look up at the night sky and see those points of light, those distant suns in a galaxy that's part of a universe beyond imagination, remember this: you are part of that universe. You are the universe looking back at itself.